remind you where we left off last time. So we had we were studying 2-1 factors of finite index, and you remember the index was the dimension measured by n of the L2 space of M, or M itself, purely algebraic definition. All right, so what we had considered was this basic construction. Now, I didn't say very much about it. Let me say two more things about it, which are really the two key things in this basic construction. So first of all, if you take an element of M, this one here, and then you sandwich it on both sides by E sub n, then it has the effect of producing for you the conditional expectation onto x times En. So remember that En and big En and little en are basically the same thing. This one is thought of as going from M to N. This one is going from L2 of M to L2 of M, projecting onto L2 of N. So this is a sort of a bit of a tautology, but it's a rather important tautology. So that's one thing. And the other thing is that if you take the intersection of if you take the elements of M that commute with En, then that's exactly N. These are the two sort of really important facts about this this basic construction. So there's two. One is that the way that En interacts with elements of M, and the other is the fact that En actually commutes with N. Okay, it commutes with N, and also N is exactly all of those elements of M that commute with the En. This means, in particular, En equals N En, all N belong to N. Okay, so this is two statements. This is this statement, and second, if this relation holds for an element of capital M, then it's actually N little n. Right, so a consequence of this one is that M equals, basic construction equals M. So if you take linear combinations, the point is that if you take x, En, y, and multiply it by z, En, t, then using these relations you get something like x, En, y, z, En, t. So the things of this form an algebra, and in fact you can show this ideal, and since a 2-1 factor is simple, you get this conclusion. All right, then very rapidly I pass to iterating the basic construction. So we form MK plus 1, basic construction MK minus 1. So we start off with M containing M containing M2, this is containing M3. So we get power 2-1 factors. And I told you last time, we sort of ended last time with the three relations on EIs. This was nothing but the fact that the conditional expectations are orthogonal projections. This is just a translation of that. The second one is EI equals EJ EI if 1 minus j is greater than or equal to 2. So let me say where this comes from. It comes from basically something we've written on the board, namely, in fact, it comes from precisely this relation here. When you do the basic construction, so here I've added a projection, I've added E2, I believe here. When you do this, the stuff that was back here commutes with this E2. Right, so as you're doing this tower, at this stage you've added, well, let's go up one more, just for fun, M4. As was pointed out, the subtlety here is that you're changing Hilbert space all the time, so you need to work with these relations in the ambient Hilbert space. But so if here I've introduced E3, all right, then E1 was back here. Okay, so it's in this algebra. So therefore, by this relation, it actually commutes with E3. So this relation implies this one. And the third one is EI plus or minus 1, EI equals. And I'm going to introduce this number tau EI. And tau is the inverse of the index. Okay. So this actually, if you think about it, follows immediately from this is E. This might be EI plus 1, EI. Anyway, this is an exercise from these relations. And then the fourth property was this thing about the trace of the word. En plus 1 equals tau trace of W. There's a word. In other words, if you take a word on the first n of these e's and then you multiply it by the next e, then it just multiplies by trace. So kind of independence, yeah.
The relation 3 is not quite the Braid relation.
It isn't quite the Braid relation, right? I'll come back to that in today's lecture. So the plan for today's lecture is to study the Braid group and the relationship with this, but I just am psychologically incapable of leaving these EIs behind without showing you a few of the really neat calculations that you can do with them. Okay, the Braid group is one thing, but there's all kinds of other beautiful things. So I'm going to get even further behind by doing a few little computations with these EIs. So the first one I want to do is prove for you a theorem called Goldman, which existed, I guess it was the early 1960s. So I'm going to give a proof of this coming from this philosophy, and it says that if m, the index of m and n is 2, then m is the fixed points. Remember I said that these subfactors are sort of, there's some kind of analogy with Galois theory and groups and so on. So this is an analog of really, if I expressed it slightly differently, in fact that's the way the proof will go, that a subgroup of a group of index 2 is normal. So this is the moral analog of that. Moral analog. Will sort of be quite simple, and we'll just use our EIs here and the relations that we have on the board. So I'm going to cheat just a little bit, but it's not too hard to fix it up. So the point is that what I want to focus on also, this proof has the advantage of focusing on the key ingredient that's going on. I want to look at this element E1 sup E2. Right. So if you have, so there's two ways to think about this element. It's, if you have two projections in Hilbert space, then you take their linear, they project onto subspaces, you take their linear span, take its closure, and take the projection onto that. That's one way. So this is projection into linear span. Closure. So this is a very standard notion in geometry. Another way of thinking about it is it's the identity of the star algebra. Generated by. So let's meditate on this for a moment. What is the star algebra generated by E1 and E2? You see, you don't really understand anything about these EIs until you do this calculation. So let's do it. Let's start multiplying these EIs together. So we start with E1. We multiply it by itself. We get back to E1. If we multiply it by E2, we get E1, E2. If we multiply that again by E2, it doesn't change it. If we multiply it again by E1, well, this relationship here applies. We get E1, E2, E1, which gives you back E1. So we're sort of stuck in terms of getting anything more. Now, we're also supposed to take stars, so we could have E2 and E2, E1. Generate those. And now, if you just look at that, you'll see that, in fact, these relations force this to be closed under multiplication. If you multiply this one by this one, you get back to one of these. If you multiply E1, E2, let's just do an example. E1, E2 times E2, E1. This is a projection, so it's E1, E2, E1, and that's tau times E1. So you'll see that this algebra that you get generated by E1 and E2 is just a four-dimensional, non-commutative star algebra. Well, it doesn't have any choice but to be the 2x2 matrices. By Wedderburn theory, by direct explicit writing down matrix units, by any way you like. There's only one over the complex numbers, two-dimensional, non-commutative, four-dimensional, non-commutative star algebra is 2x2 matrices.
So you add one is always a number.
No, I've very carefully left out one.
But then how you know it's a matrix algebra is not evident. I mean, you need to know that there's a unit.
Semi-simplicity takes care of that. So if you don't like my intimidation proof, just write down for yourself the identity. Well, we can do it. Okay. Here we go. Here's an exercise for anyone who wants to do it. Exercise. 1 over 1 minus tau times E1 plus E2 minus E1, E2 minus E2, E1 is identity. Okay, well, this is not very hard to check. All you have to do is check that when you multiply it by E1 and E2, you get back the same thing. On the left and on the right, but that's a simple exercise. Okay, so let me set that as an exercise for any students who are doing this course. It's very easy, doesn't take very long, but it's extremely revealing, the whole structure of everything. Because now let's suppose that the index is 2. That means tau is equal to 1/2. Okay, and let's take the trace of this guy. Trace of this guy. Well, the trace of this guy, let's call it E1 sub E2. No matter what we call it. Well, it is 1 over 1 minus tau is 2. The trace of E1, that's the index, that's there all along, that's tau, which is 1/2. This one is 1/2. This one, by this relation here, is 1/2 times 1/2, which is 1/4. one is another a quarter. So altogether, these ones cancel. We get 2 times a half, which is equal to 1. All right? So we have a, but you see, we're in the 2-1 factor. Remember, this trace is positive definite. So the trace of 1 minus E1 sup E2 is therefore equal to 0. But E1 sup E2 is a projection, so it's less than 1. So this trace being equal to 0 means that E1 sup E2 is actually equal to 1. Okay? It's amazing. So E1 sup E2, which in general, with just the identity of this part, the more, if you, the point is that if you throw in the identity, you're actually going to get an algebra 1 dimension bigger. But in index 2, that identity, that 1, has to actually be equal to E1 sup E2. There's actually a relation between E1 and E2. E1 E2, very simple relation which says that 1 is equal to E1 sup E2. Now here's another exercise. Just check. This is equivalent to 1 equals E1 sup E2 implies 2E1 minus 1 is 2E2 minus 1 is 2E1 minus 1 is minus 2E1 minus 1. Okay, it's just a simple exercise. You just expand it out. There's 8 terms. You use the relation, cancel a few out, you get this. So if we call this one U and this one V, U squared is 1, V squared is 1. These are self-adjoint unitaries. U equals U star, V star. And UV equals minus VU. Okay. Nothing but an exercise.
Is it, can you say a 2 there instead
Sorry?
of 1? Is it a 2 instead of a 1 in the last?
2E1 minus 1.
So it would be 2, 2?
2E2. Should be 2. Thank you. This is terrific because now I'm actually going to prove it. As I said, I'm going to cheat here. I'm actually going to prove that M equal to fixed points under an action of Z mod 2Z. Okay, but there's some kind of generic structure of the basic construction which allows you to push that one back and get the original result for M. But, so this now we can see, because if we take M, we know that M is equal to M. Sorry. What I set up here, MEN equals MENM, which is the same thing as M times U U M, right? U is just 2E1 minus 1, so to use 1 or M here is the same thing. So, and the point is that V commutes with M. It's one beyond the basic construction. So we have, if we take X, U, Y, and we commute this with V, we get minus X, U, Y. So conjugation by V, this is the same thing as V inverse, V star. Conjugation by V fixes M, it's the identity on M, and it takes MU, and it takes, what am I saying here? Am I saying this right? I guess I'm not saying this right, am I? Got this wrong. MUM, that's not quite innocent. MUM not equal to, sorry, I have to do this slightly different. This is a lesson in detail. It doesn't work. change this relation to mu e2 to b e1 e star unknown. So here's what I want to do. I want to write m equals m plus m. Let's do this. M en equals m plus mu. That's because m en is m times 2e minus 1. Help me a second. This is true. This is x plus y. Oh well. I have to. Sorry, I have to. U normalizes m, right? But right, that's right, yeah. You have to, I think you have to work slightly harder. So let me push this. And this, then we use this property. There are certainly all the ingredients to check that. Oh, well, actually, that's it, isn't it, really? Yeah. In fact, I'm making life much more complicated than I need to. I don't even need to do this. Okay. So let's, although this is true, I think it's silly. I'm just going to waste time fixing this up. There's more than enough ingredients on this board here to deduce this if you sit down and think about it carefully for 10 minutes. All right, but now what I'd like to add to this is that Izumi is, I appeal to Izumi for good reason, in that Izumi has proved quite a long time ago an extension of Goldman's theorem. Index 3. Not 3 factorial, index 3. And this is a really nice theorem. And the result is slightly different. Because as you know from group theory, there's two situations. If your group of index 3 is normal, then it's just you know, it's either normal, in which case there's a well, okay. Let me just say there's two cases. A n is the fixed points for z0 3z. You can't quite say this for groups. And B, n is equal to there's some other factor p, so that n is the fixed point algebra for an action of the symmetric group on 3 letters. M is a p fixed points under S2. These are obviously included in one is included in the other. So this is like a non-Galois extension. We have a non-normal subgroup. S2 is a non-normal subgroup of S3, so we have a non-Galois extension. So this was a really nice result at the time. Azumi was ahead of the crowd in understanding what has now become known as the fusion rules, and nowadays this would be an easy exercise relatively easy exercise in understanding the fusion rules. Actually, what's not quite so well, part 3 is a little bit harder, right? You've got to somehow exhibit these, the S3 and S2 and the action on them. I suppose that this was one of your starting points for going off onto your Kunst algebra stuff. This was a very simple first case of the Kunst algebra stuff. So it was a really nice theorem with a big future. All right. So, having done all that, so forget the details. The moral of this story is that there was this relation here, this algebraic relation between the EIs, which was forced by the trace of the E1 sup E2 being equal to 1. Now what happens in general focus on E1 sup E2 sup E3. Right, so once again, we have these EIs, we look at the algebra that they generate, we don't throw in 1. We say that's a star algebra. It's semi-simple, so therefore it has an identity. And that identity is the same thing as the supremum of these projections as projections onto Hilbert space. Okay? And the point is that as n increases, these projections are getting closer and closer to 1. In index 2, we saw that they hit 1 right away. So if the index had not been equal to 2 and we'd done this trace calculation, we would have got something strictly less than 1. Okay? So therefore, it's a really good thing to look at, to call this, to take the difference. The thing that's getting small is what we call Fn, which is the difference between the supremum of these Ens and 1. And since by an exercise these relations suffice to calculate traces of any word, we should be able to figure out what the trace is of 1 minus 2 minus En. And indeed we can, and we find that's some polynomial in tau. Polynomial in tau. It has to be a polynomial tau. Well, maybe it's not quite so obvious. You do an inductive proof, you find the relationship between the supremum of the first n and the supremum of the next n, and you find that that's polynomial in tau. And in fact, the polynomial satisfies this relationship. n plus 1 of tau, n of tau. It's a second order difference equation in tau. And in these polynomials, and that's just a reflection of the fact that this tau here was defined as a second order difference equation in the 2-1 factors. All right, so now to see why these index values is 4 cosine squared pi over n, to see how they come up, I want to actually do a very hands-on picture of that by just drawing the graphs of the first few of these polynomials. This is, I think, the most beautiful part of the whole theory at this stage. We're just going to graph these functions. So let's examine the first couple. So Pn, what's P0? Let's start off with P0. What's F0? Well, F0, there's no EIs, so F0 has to be 1. So F0 is 1, so P0 tau is 1. Now what about P1 of tau? Well, for P1, there's 1 E, so it's the trace of 1 minus E1, which is 1 minus tau. So P1 of tau is 1 minus tau. Let's just do the next one. P2 of tau, which we could easily get by taking the trace of that formula that I just erased. Well, since we have the relationship here, this is by the difference equation. It's P1 of tau, 1 minus tau times 1, which is 1 minus 2 tau. And I'll save you the trouble, I'll do the next exercise. P3 of tau is 1 minus 3 tau plus tau squared. And so on. It's obviously very easy to figure them out. But now I want to draw the graphs. We're really interested in tau values between 0 and 1. So here's the graph of the first one. Doesn't say much. The graph of the second one is down here. 1 minus 2 tau. And the graph of the next one is they're monic, so at least this one's monic, so it's product of the roots has to be equal to 1. So one's less than 1, the other is bigger. All right, so now the point is that these values are all traces of projections. Okay, so they have to be greater than or equal to 0. So that means, so imagine that you happen to be a number between 1/2, this is 1/2, and this is 1 over the squared. So imagine that you're a number sitting here between 1/2 and 1. Well, you read off the trace of the corresponding P, the corresponding projection, and you're negative, so you're not allowed to be. There's nothing between 1 and 1/2. If you're a half, well, the trace is 0. That doesn't say anything bad. Well, it doesn't say anything impossible, and that, of course, corresponds to that relationship between E1 and E2. So there's no particular conclusion. There's no particular conclusion, but one bad thing is that you cannot go on to apply this to the next formula, because that was, you know, relying, this thing is, relies on the fact that the one you've got up to there is actually an honest projection. Okay, so now what happens if you're in this interval here? Okay, well, your trace, the trace of the corresponding P, 1 minus P1 sup P2 sup P3, I guess it is actually negative, so you can't be there, sorry. The next allowed value is this one here. And if you continue to draw graphs of these things, you'll find that they all start off like this and they converge to quarter. So the conclusion is that if you're in between a quarter and 1, unless you're on one of these points where it actually hits the x-axis, you're dead. So all of these intervals here are eliminated from consideration, and we find that tau equals 1 over 4 cos. The exact value is not very hard to obtain. This is just a simple second-order equation. It's some kind of shifted Chebyshev polynomial, and you know everything about those. It's very old mathematics. You find very simply that the smallest 0 of one of these Chebyshev polynomials is actually 1 over 4 cos. So that actually proves the index for subfactors result. It's really kind of cute. Just look at these graphs and see that if you're in the bad region, then there's some trace of something becomes negative, and on Hilbert space, since the inner product is positive definite, that's not done. Okay. See where I am there. So maybe just, I'll go out of order slightly, because of, maybe we're getting a bit sick of these on limit algebras all the time. So let's answer this question about the braid groups. Then we'll come back to this. So I really do want to come back to this, and there's a very good reason, and that is that all we've used out of this tower, we've constructed this giant tower here, and all we've taken out of it is these DIs. And later on we'll come back and take some more out of it. Let's just switch branches of mathematics for a little bit for a change and talk about the braid group and this relationship between braid group and the DIs. All right, so if your brain was nearing saturation with von Neumann algebras, you can switch that all off and start again. So I'll emphasize that by changing the color of the chalk. Totally new start. So the braid groups Bn are certain nowadays very popular well-known groups in mathematics. They were not so well known in the early 1980s. And they basically have three lives. I'm going to talk about two lives, the most different lives that they have. And the first one is as a group generated relations. This is in the theory of what you would call combinatorial group theory, where you write down some generators, write down some relations, and look at the group that they generate. So here it is as a group generated relations. There are n-1 generators, sigma 1, sigma 2, sigma n-1. And there are relations, which I'm going to call sigma I, sigma j, equals sigma j. So if the indices are 2 apart, they commute, and of course you'll observe immediately that is rather similar to that. And then we have to say what happens if they're next door. And for various reasons, which sort of occurred over in the subfactor world as well, Bn has n-1 generators. So this is life number 1. So let's just go and explore the braid group before we talk about life number 2. Explore it in terms of generators and relations. Well, I suppose the most obvious thing to observe is that B1 is, B2. B1 is B1. Well, this is the theory of the empty set. There's no generators and no relations, so that would be the trivial group. Okay. B1 is the trivial group. B2 is when it starts to get interesting. Here's one generator, sigma 1, and no relations. None of those apply, so B2 is equal to Z. And then you can also say something about B3, and B3 has is just sigma 1, sigma 2, sigma 1 equals sigma 2, sigma 1, sigma 2. And if you do a little exercise, you'll find that sigma 1, sigma 2 cubed is in the center. It's just at this level. It's just a little bit of fun playing with these generators and relations. So therefore, when you quotient out by B3 by its center, and you look up any book on lots of different areas of mathematics, you find that this is. of Z mod 2 and Z mod 3, and you
Here's the element of Z mod 3.
sitting right there. And the other one is sigma 1, sigma 2, sigma 1. That squared equals the identity. Because, see, let's just do this. This is the only exercise I'll do. Sigma 1, sigma 2, sigma 1 is the same as sigma 2, sigma 1, sigma 2. So if you take it squared, you get sigma 2, sigma 1, sigma 1, sigma 2, sigma 1, sigma 2. And that's the same, re-bracketing it, it's the same as sigma 1, sigma 2 cubed. So you have something whose square is equal to 1, something whose cube is equal to 1, and just by exhibiting enough homomorphisms, you actually conclude that the braid group is equal to that. Okay? So it's a group that just in terms of generators and relations, we know that the B2 is Z, B3 is some central extension. In fact, if you look a bit harder, you'll notice that you have SL2Z. PSL2Z is contained in the Lie group PSL2R. That being a Lie group has a universal central extension, and the universal central extension of that is by universal covering space is by Z, and this extension is just the pullback of the universal covering of PSL2R. B4, well, B4 is, I don't really know what it is so much, and B5 even less so. There's actually a theorem that says that you can get these BNs as iterated semi-direct products of actions of the braid group on the free group. But that's better understood when we have picture 2 of the braid groups. Okay. Any questions about the braid groups as abstract groups? I guess there's one thing that's not entirely obvious, is that Bn is a map from Bn to Bn plus 1. Right? We just add one more generator. Now, a priori, that could not be injective, but it is injective. Another thing that you can check on the, with standard tools from combinatorial group theory. So you have this tower of braid groups. Just all some kind of combinatorial groups, generators, and relations. All right, now I've deliberately not done any topology yet because I just want to line up these generators and relations. And as was observed, this relation 3 is not the same as relation, as the braid group relation. Okay? So if you wanted to represent, so what you might want to do is represent the braid group linearly inside this algebra business here, inside this factor world. Well, one thing you cannot do is you can't just signify the ER. But, that's not hell of a surprising. I mean, if you're looking at group representations, you wouldn't be representing groups by projections, and these ERs are projections. But what you can try to do is to try to take a linear combination, say X times the identity plus Y times EI, and send sigma I to that. And the question is, does that work? Now there's a simple calculation, which is another exercise. Which says that there is essentially one value, obviously everything's defined up to scalars, and there's essentially one value of x and y, which is really one value of y, which makes it work. And the value, of course, will be determined by this value over here. So the theorem is, the exercise is, this gives a braid group representation and only of scalars
have T EI plus 1 minus.
1. You write it out, and it's like this.
Form. Reveal and form.
I'm doing a slight change of variables. I said x times the identity plus y times EI, and here, but there's a total freedom in rescaling both of these, so I've rescaled it so that y is minus 1. You'll see there's good reasons for doing this. And the main good reason is that t works out well in terms of tau. So tau is t. So here's the exercise. If you write this element here with t as an unknown, and you ask that it satisfy the Braid equation, then you find that it's true if and only if t and tau are related by these two formulas here. Okay. And another way of writing this is 1 over tau equals 2 plus t plus the inverse.
Let's just do a little bit of numerology with 4 cos squared pi over n. So 1 over tau is
The index, and this is
2 plus t plus the inverse. And this is 1. This is root t plus 1 over root t squared.
and this could be, the interesting values of this was 4 cos squared pi over n. So lining these up, we get 2 cos pi over n equals root t over root t.
And this
Of course, is e to the pi I over n plus e to the minus I pi over n. So the conclusion is basically, up to some trivial switches,
is that root t is e to the pi I over n. So t is e to the 2 pi over n. Okay, so
this
this
shows you why this is such a good choice of values.
we find that for this
Subfactors of index 4 cos squared pi over n, we've converted 4 cos squared pi over n into a root of unity, not just any root of unity, but the
not just the primitive one, but
the most the closest one to 1. T equals e to the 2 pi over n. Okay, so
and moreover, in terms of this representation, we have e to the 2 pi I over n. EI minus 1 minus. The real advantage
of this, of writing it in this form, is that you remember that EIs are projections, so if you had a representation in matrices, you could
diagonalize them. You have this thing, e to the 2 pi over n down the diagonal all of the times, and then minus 1.
If I diagonalized EI so that it was a bunch of ones and a bunch of zeros, then this is what, in that basis, this is what one of these Braid generators would look like. So in particular, they're unitary. So for what it's worth, what we have created here is a family of unitary
finite dimensional representations of the Braid groups.
Why do I say finite dimensional? Finite dimensional because I guess we've never really done this, but so maybe now is time to do this while we're still at this level. We've still got these relations fresh in our mind, let's check.
So let's go over here and have a lemma.
The lemma will be that these relations
Imply that algebra generated by one the dimension is not only is it finite dimensional, but the dimension is less than equal to one of them plus one.
Well, this is just a matter of showing that there's some kind of reduced words for when you start multiplying these EIs. And it follows from
any word contains Emax.
So this is what you might call the fundamental piece of combinatorics for the algebra, this so-called Temperley-Lieb algebra. So what do I mean by this? I mean that if you have a, well, when I can just sort of prove it as I stated. Suppose you had a word that had Emax in it more than once. We have a word which can, Emax is the maximum index of the EIs that you see there, right? It's obvious. I mean, suppose we had a word that was W1, Emax, W2, W3. Okay, I'm in the process of proving this. Well, W2, we might as well choose an occurrence. But what we want to do is show that we can get rid of this Emax. Get rid of, use these relations to get rid of one of the occurrences. Well, W2, we might as well assume that it doesn't have any Emaxes in it, just by choosing the two ones close together, as close together as possible. So what's W2? Well, that's something on E1 up to Emax minus 1. Okay? Well, by induction, that's going to be, say, V E max minus 1 prime. Right? Where V and V prime now are words on everything up to Emax minus 2. Okay, but Emax will commute with them, and it will commute with them, and you'll see V prime, Emax minus 1, Emax. And by this relation, we get rid of that, and we get W1 Emax minus 1. So we've got rid of one of the occurrences of Emax. Okay. You might say, what if Emax minus 1 hadn't occurred at all? Well, that's even better. In that case, there's nothing in there that stops us commuting this Emax all the way past and using this property. So it's certainly finite dimensional, and a little bit more work shows that by induction you can get this Catalan number estimate for it. So therefore, the algebra generated by these EIs is a finite dimensional star algebra. So these representations, you've got something semi-simple. The representations are therefore finite dimensional representations of these EIs, the ones that you get. Okay. So that's pretty neat. You can examine them a bit, and if you do, you find that you might ask me, what's the relationship between this braid group representation and those ones that we did in proven Goldman?
2e1 minus 1, 2, 2 minus 1, 2, 3 minus 1, 2, 4 minus 1.
Are these the braid group elements? Well, no, they're not. These ones satisfy, this gives you what's called an extra special group, and the braid group representation is slightly different because T there, the index is
4, is 2, so we've got 4 cross group 5 to 4, this is I. The braid group gives you I times E. Square root of minus 1. E of I minus 1 minus 0.
But these, of course, do interact, and you find that you can get in this way the structure of the image of the braid group in index 2 has something to do with an orthogonal group. Well, it's actually it's quite simple. It's some kind of extension of the symmetric group by Z mod to some power. Okay, so this can all be figured out by simple calculations. In index 3, so is Umi's special value, the thing gets really neat. The braid group representation ends up being essentially the symplectic group 2 and L3. Which is pretty close to being a simple group, so you actually get a family of, very easy family of simple groups coming as the images of the braid group from these representations. So what I want to say is purely on the level of groups given by generators and relations, we've got kind of an interesting family here of unitary finite dimensional representations of the braid group, whose images can be finite groups, but you can easily check that if you for cluster 5, you put n equals 5 in here, then the images are not finite at all. The images actually end up being dense. It's been shown in detail by people doing quantum computing, Friedman, Kataev, Larson, and Wang, that these images of the braid groups for the most of the time are actually infinite dense subgroups of the corresponding unitary group. Okay, so I'll stop here for the 15-minute break, just with this thought that we've got these representations which are interesting just from a purely algebraic point of view, knowing the braid group as generators and relations. And then when I come back, I'll give the second life of the braid group, and we'll have the connection with knot theory. So it's and we'll think about the other life of the braid group. Two. This is from the movies, right? You have to, making a movie, you have one shot and then stop and then take two, second take of it. We're going to have another look at the braid group. So this is a mechanical, actually quite mechanical point of view. A braid on n strings is the following device. We have two horizontal bars with n points on the bottom bar, say. Here n equals 5, and the same end points, the second bar is sitting straight above the bottom bar, so we have these points which are lined up, and then the points on the bottom are joined to the points on the top by the strings. So the strings are bits of string. Allowed to do pretty much anything they like, except that once a string starts going from the bottom, it always goes upwards. It never turns around and comes back. So if you like, the vertical, the tangent to the string, tangent vector to the string always is non-zero vertical component. Okay, so the string starts going up here and it keeps on going up until it gets to the top. Right, so that's a mechanical device, and you can imagine getting a bar and pieces of string and just tying them the top to the bottom. So the mathematical object corresponding to that, of course, we assume that these, this is a straight line in R3, this is another straight line in R3, and these strings are smooth curves. So these are C infinity curves in R3. Now, what do we mean by two braids being equivalent, equality of braids? Well, in the physical sense, if the strings are sufficiently loose and elastic, it just means you can stretch them or push them and so on, do all kinds of things, as long as what you're doing happens in between the bars. Well, you're not allowed to take one of the strings out and bring it around and bring it around the other way. So equivalence, so mathematically that becomes isotopy, smooth isotopy. Isotopy between the bars. So there we have a set, a mathematical set of equivalence classes of systems of curves, the bars and the smooth curves joining the bars top to bottom. Bn, so Bn is the set. Equivalence classes, isotopy equivalence classes. The scaling doesn't matter because you can get them by stretching, and these crossings can be moved around and so on. Doesn't matter very much as long as the isotopies happen in between the bars. Right. So first remark is Bn is a group. So this is Bn take 2. Is a group. And the group operation is obvious. If we took concatenation, if we took one braid here, and another one, let's just do 3 strings to be a bit more modest. Walk. We have any old braid here, say that one, and any old braid here, say that one. Then we just stack this second braid if this is alpha 1, or if this is alpha and this is beta. Then alpha beta is what you get by stacking like that, and then you take away the middle bar. Okay. So that's a group operation. On the level of, this is well defined on the sort of generally accepted topological level of rigor. If you isotope either of these two in between the bars, then the isotopy will extend here, so you'll get the result, the product is well defined up to isotopy. You can rescale it. Now the fact that it's a group, of course the most obvious thing about the group is the identity. So here's the identity braid. Oops. Consistent with the colors. On 3 strings again. It's completely obvious that up to isotopy. If I concatenate any braid with this, I'm not going to change it. Inverses, or associativity is, just draw the picture of associativity and it's obvious. Inverse is slightly less obvious, but the simplest way to see it actually is to have a mirror. So if I have a braid, some kind of braid here, a whole lot of strings, and then I set this braid, so this is a drawing room proof. I set this braid on a mirror, and I look in the mirror, then what I see is I see the reflection of the braid here in the mirror. And if I look at it, I'll see this, the braid that I see in the mirror, I'll just see it undoing this braid here all the way to the top. So it's a group. All right. Now, the next step is to make the connection between braid group take 2 and the other braid group. Well, we've got to get some generators, well, some obvious generators. So if we have 4 strings, let's make 5 strings to get the notation going. So we can have a braid which simply does a single crossing in between 2 strands, 2 points like that. And there's like the identity everywhere else. And there's one of these, you'll notice that these, if you number these points 1, 2, 3, 4, and 5, then how many of these are there? Well, there's 1 for 1, 2, 3, and 4, but we can't go beyond it, so not enough points. So this one we call sigma I, and here I is equal to 2 in this example. So in other words, sigma I in general is a braid with a crossing between the ith and I plus 1th points. Right? Now relations. So why does this generate the braid groups? Well, it's quite clear that any braid, you look at it, it's given by the sequence of crossings. And you can simply make sure that these crossings by a little isotopy, if the only bad thing that can happen is if these 2 crossings actually occur on exactly the same level, but you can just push this one up a little tiny bit, push that one down a tiny little bit without interfering with anything else. So we see that any braid is actually a sequence of a crossing here and then a crossing somewhere else, and a crossing there and so on. So it's actually a word, manifestly a word on the sigma i's and their inverses, depending on whether the crossing is over or under. So certainly the braid group is generated by these sigma i's, and the relation sigma I, sigma j equals sigma j, sigma I minus j is greater than or equal to 2, is obvious. In fact, it's just exactly what I said in terms of if we have a crossing here and a crossing that's distant from it, then you can push, you'd have sigma I followed by sigma j, or sigma j followed by sigma I. The relation sigma I plus 1 sigma I equals sigma I plus 1 sigma I plus 1 is a simple picture which we might as well draw since we're in the mood. It's in the 3-string braid group. I'll be sloppy about the colors now maybe. This is sigma I plus 1, sigma I. And then on the other hand we can do sigma I plus 1, sigma I plus 1. And if you look at these 2 pictures, you can see that they actually are isotopic braids. You can just you can pull one in the middle through the center of the other 2, and it converts one to the other. All right, well that shows that there's a homomorphism. This is a universal group of these generalizers and relations. So we get a homomorphism from Bn to Bn take 2. And the highly non-trivial result of Emil Artin shows that this is an isomorphism. Okay, so this actually requires a fair bit of proof and actually goes through, typically goes through the this iterated semi-direct product of braid groups and free groups and the interaction between braids and free groups, which you can. Well, that's a fairly long story, not all that deep, but it's not easy by any means. There's a key player in the whole thing, which is the homomorphism. There's an obvious homomorphism from Vn to the symmetric group, Sn, which is each braid defines a permutation on the endpoints. And the pure braid group, Vn, is the kernel of this. So it's the braid such that this point ends up coming back to that point up there. Another thing you can see rather easily, actually, with this geometric picture is the fact that this sigma 1, sigma 2 cubed is in the center. That was just a question of playing with the relations, but you can see that in general, sigma 1, sigma 2 to sigma n minus 1 n, this braid is actually a 360-degree twist. Okay? Just draw it out, you'll see that everything comes back and it's all done. So now it's obvious that that's in the center of the braid group, because if you have a braid here, okay, alpha, and then you have a 360-degree twist, then you just sort of lift this braid here as you're going around, keep on lifting it, and at the end it's come out the top. Okay? So this braid times this full 360-degree twist is the same thing as the thing in the other direction. So there's all kinds of cute things that you can see geometrically that might be quite hard with generators and relations. Well, perhaps less fun. Sometimes it's fun to do these long algebraic calculations. See all of these cancelling happen. I mean, doing that proof that this is in the center, you have to work a bit if you want to do it algebraically. Okay. Right. So you notice that this this pure braid group, there's an extension. There's obviously an extension from the pure braid group to the braid group to the symmetric group. It's certainly not split. There's no way you can lift the symmetric group up to the braid group. In fact, the braid group is torsion-free. Right? You start twisting and keep on twisting. You're never going to undo anything as long as you twist the same way all the time. So that's a nice extension. It's far from being a symmetric group. Okay. Any questions about the concrete braid group? Okay, so now let's see how it interacts with this homomorphism that we defined, these unitary representations that we defined inside this algebra here called the Temperley-Lieb algebra. Well, the fact is that we have so far used only the relations 1, 2, and 3. The trace on this algebra that exists, we know it from subfactor theory, was completely absent in the discussion over here. This mapping here, sigma I going to T EI minus 1 minus EI, that gives a braid group representation. That was, we never used that fourth relation. It just simply wasn't there. Okay. By the way, hopefully you'll have time to actually start decomposing these representations into reducibles a little bit. It's rather interesting. But anyway, let's see how this trace relates. And the key here is that there's a relationship between braids and knots. Braids and knots. And this is very simple also geometrically. If we take the braid group, take 2, so the geometric picture of the braid group, we have a braid, blue, red, and yellow. So I want to actually do a specific one. Reasons best known to myself. Let's look at this braid. That's not the one I want. I want one more crossing. So just as an exercise, everyone to do on the spur of the moment, on the fly right now, let's write this as a word in the braid generators. Okay? So what do you do? Well, the crossings have to be in general position, which they are. One here, one here, one here, and one there. And then to write it out, you just sweep up and then record the crossings as we go. So this becomes sigma 1, sigma 2 inverse, sigma 1, sigma 2 inverse. Okay, so that's a nice braid. All right, now the connection between braids and knots is that there's this thing known as the closure of the braid. If we call this braid alpha, then alpha hat is simply obtained by taking the, I can't quite bring that down. So I haven't hidden anything here, that's the lesson. Nothing happens behind this, just goes behind the board and then comes down. Nothing fancy, I haven't cheated. So all we've done is we've tied the top of the braid to the bottom and then we remove the bars, like we did in the multiplication group structure. Now there's no bars left, so we get a closed curve in 3 space. These things were smooth curves, smoothly contained, and so on and so on and so forth, so we get a knot. Where I'm assuming that we know that the definition of a knot is a smooth closed curve in 3-dimensional space. At least we get a picture of a knot. So in this case, the reason that I chose that particular braid was that this is a well-known knot that we get. It's the so-called figure of 8 knot. If you stare at that for long enough, you will see that you can make this diagram into that diagram. Okay. Right, I said a knot. Well, in fact, there might be more than one component, right? What if I just had another string going up there and then close that off there? Well, there might be more than one component. They might be all interlinked. So in general, you get a link. Where by link, I simply mean a knot, but with several components. So why did I get a knot and not a link with more components than this one? Well, obviously what it has to do with is the permutation of the endpoints. You get as many components, the link has as many components as there are orbits of the permutation of the endpoints. Because if you take an orbit of that permutation, then if you go from this point to this point, you're on the same string, and then you come around, you're on the same thing, and so on. You get as many, it has as many components as there are orbits. So for instance, if you took this full twist, let's just do it, sigma 1, sigma 2 squared, and you close that one, sorry, this is sigma 1, sigma 2, and you close that one, and you get 2 components. This is a link with 2 components. And if you did that full twist on the 3-string braid group, you would get a link with 3 components. And in general, the full twist with n strings, you get n component link. Right? So the first question that you ask yourself about this correspondence from braids to links is it surjective? Because if it is surjective, if you can get any link in this way, then maybe you can use the braid groups to say something about links. And that could be very useful because braid groups, after all, are a group. It's a group structure. Whereas links do not have any kind of group structure. So the first theorem due to Alexander American mathematician Alexander, is that any braid, any link in R3 is of the form alpha hat for some alpha and some bn. So this was alpha hat. This closure of the braid. So any link can be obtained as a closed braid. So this is actually not all that hard to prove. You just have to take a link and sort of fiddle with it a bit until you come up with a picture which looks like this. So maybe one of my exercises should be, I'll give you a specific link and you have to make a braid out of it. That's a good exercise. Close braid out of it. Actually, I should, if I'm going to do that, then I need to give you a hint on how to do this. So let's suppose that we started with this figure 8 knot. We wanted to turn it into a braid. And the very first thing to observe, which I haven't said yet, is that this whole process is oriented. Okay, the fact that the braid, remember, braid has to start at the bottom and keep on going to the top. Well, that means that you can canonically orient a braid, all the strings of a braid, on the way around. So the first thing we do to start to turn a knot into a braid is we, whoops, made a pretty bad start there, didn't I? That's a terrible start. As bad as can be. So this one going around here, then that one gets removed. The point is that if it is a closed braid, then there's this point in here, and with respect to that point, the string just keeps on going round and round and round and round clockwise. And if you think about it for 10 seconds, that's all you need to do. All you need to do is find a point somewhere inside the picture such that it's always going round and round clockwise, because you can take any point where there's no crossings and sort of spread that so that the in between, isotope it so that this is the part in between no crossings, and then make it all the way up here. So the job is simply to find a point in that picture so the braid is always going round and round in the same direction. Well, there's a couple of obvious choices. That one there, for instance. If we start here, it's going round and round and round. Oh, all of a sudden there it's gone bad. So in between there and there, it's gone bad. Right, so from about here to about here, it's bad. No, from there, turn around. That was not, well, this I'm sorry, let me switch to this point. We could have used that point, but the picture I'm going to get would have been a bit more complicated. So now, let's see, we're going around the right way here. Whoop, between there and there, it's bad, but then it's round the correct way. So we've got to do something in between here and here. What you do is you simply sort of throw it over your shoulder. So we fix this up, taking this part of the string, making that go around there. Now you'll see the string is going around the right way all the time. So you can read off the braid by taking some of it here and making that the back of the braid. When you get a version somewhat like this. Okay. So with having shown you that, I'm going to make an exercise for you in the exercise list for the students of a link that you're going to turn into a braid for me. All right. So now the question, of course, the immediate question is, we have this mapping which takes the braid groups to knots. And it's surjective. You'll notice that the more complicated the knot is, the more strings you're going to need on the braid. There's no one of these braid groups that you can use to get all knots. You need to use them all. So we have an equivalence relation, therefore, on the disjoint union. We take the disjoint union over n of all of the braid groups. We can say x is equivalent to y, but only if x hat equals y hat. Okay, as knots, as links. So this set, the disjoint union of the braid groups divided by this equivalence relation, is equal to the set of all links in R3. Okay, that's Alexander's theorem plus tautology, plus just defining it to be that way. All right, well, so obviously if you want to use the braid groups to study links, then you're going to have to understand this equivalence relation better. In other words, when the two different braids give the same link. Well, if you think about what we did in this machine where we turned a knot into a braid, then there was, once we got it all going around and around, there was ambiguity about where we would start. This where's the back of the braid going to start? And once you've decided that, then there'll be sigma, 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 sigma as it goes around. So this translates into a rather obvious so-called Markov move. And that is, if you think about it for a bit, you'll see that this ambiguity in where you start the braid is just the same thing as conjugation in the braid group. So alpha belonging to Bn, going to beta alpha. So we take a braid and we produce another braid in the same braid group, and that's the move. And of course, it can go both ways. It's completely symmetric anyway. Right, so the claim is that if you change alpha by a Markov move of type 1, then you don't change the braid, the knot. So it's saying this. And you can see that pictorially quite easily if you take alpha, beta inverse, and then you close them around the back. You can simply take beta and bring it around there, and it would simply annihilate with itself when it comes around the other end. So now type 2 move, slightly more subtle. And let's draw it here. We're going to use a braid alpha in Bn. And the first thing we're going to do with it is to move it up to Bn plus 1. We're going to add a string to it. So I guess I didn't say it, but way back when we discussed the algebraic definition of the braid group as generators and relations, there was this obvious tautological map between the braid groups, and then I said there was an injection, so each braid group is contained in the next one. Well, geometrically, that means that if alpha is sort of strings all the way out to here, then we can move alpha up into the next braid group by adding a string to the right, okay, and extending everything up like that. Then what we're going to do is we're going to give it a little twist. Okay, and now look what happens when we do the closure of this one. Well, this is going to come around to here. This is going to come around to here. There's nothing in this region here. Nothing at all in this region here, because the alpha stops there. So this simply untwists. This could have been a twist either way, a plus or a minus. So type 2 Markov move is alpha going to alpha sigma n to the plus or minus 1. And this picture has shown that alpha hat is equal to alpha sigma n to the plus or minus 1 hat. Markov's theorem is is that theorem Markov two braids give the same closure. If and only if they're connected. Okay. Now it's interesting, this will be a historical note that I'm sure Masaki will like. So when I did my work in this area a long time ago now, and I was fortunate enough to be able to talk to Bill Thurston reasonably frequently as I was doing it, and I told him at some point that I had this knot invariant coming, and I used Markov's theorem to get it. And his reaction was, great, now we're going to find out whether Markov's theorem is true or not. So there was some ambiguity, there was some doubt, I guess, amongst experts as to whether there was this theorem was really true, because it's a pretty non-obvious theorem, especially with these orientations and so on. The idea is that it's known as Reidemeister moves, which are the moves on knots and links, and they're sort of translated into conjugation in the braid group, and the inverses have to do with type 2, but they're organized in a completely different way in the braids, so it wasn't at all clear that this was true. But of course, as a result, of the interest, some much simpler and more accessible proofs have emerged of Markov's theorem.
Is this Markov in any way related to the other one?
Yeah, this is the thing that really, this is one of my favorite pieces of serendipity or something. So as I said to some of you after what we're going to do is, let me just jump ahead. To answer this question, let me jump ahead. What we're going to do is we're going to take the trace of a braid and get an invariant of knots, okay? So as I said, these conditions here are extremely reminiscent. In fact, they are strictly a kind of Markov chain. This is a non-commutative Markov chain because you have sort of independence. These EIs and EJs commute, and the only thing that's going on is a relationship between the last one, the second to last one, and the last one. These two don't commute, and you have statistical independence otherwise. So this is definitely a Markov condition, and that's reflected in the analysis, which was these second-order difference equations and so on and so forth. It was all Markov, Markov, Markov. You could have put Markov after every second word practically. So here we have Markov, who has this theorem that we're going to take full advantage of, and it has this Markov thing, right? This type 2 Markov move. It's just taking something and then tacking something on at the end, just like a Markov chain. So the question is, are they any relation? Are they perhaps the same Markov? It's sort of the same idea. They're not the same Markov, but they're both AA Markov, and one's the father and one's the son. The father, of course, is the Markov chain, and the son is this Markov, who's a noted topologist. There's some other result. I think something about the word problem is due to Markov in group theory. Right. Well, now I've said what we're going to do, so let's just do it without any further ado. Oh, maybe just a historical remark from Masaki is. So I learned all this in this trip to. I should say. I sort of knew it already. I mean, well, here's what I knew. I knew that you could get the Alexander polynomial of a knot from a linear representation of the braid group called the Bureau representation. Bureau representation. This is a German Bureau representation. I knew that there was a formula for the Alexander polynomial in terms of the characteristic polynomial of the Bureau representation. I knew that the Bureau representation was included. It's a direct summand of this representation. little part of this representation. So what I was trying to do was I knew that there were some formulas in C-star algebras for determinants coming from arbitrary traces. So I was trying to get the Alexander polynomial by applying these generalized trace formulas for determinants in this Temperley-Lieb algebra. And I was particularly keen on that because I realized that if I could do that, then I could solve the Potts model. There's this notorious problem in statistical mechanics called solving the Potts model. And if my polynomial had turned out to be the Alexander polynomial, I would have solved the Potts model. Okay, so it was really, that's what I was hoping for. However, it turned out not to be true. First of all, I was trying something way too complicated by working with these determinants associated with traces. And all I needed to do was simply take the trace of the braid because of this property. Okay, so it's kind of strange that no one had ever thought about using the characters of representations, i.e. traces, to study knots and braids because of the type 1 Markov move, which is simply conjugation. If you take the trace, that's immediately invariant under conjugation. So you've got half the job done just by saying the word character. But so let me just write out the theorem. And it's barely a theorem, it's just a computation. So if you take, let's call pi the representation which sigma I to T E I minus E I. Representation of the braid group inside the Temperley-Lieb algebra, and we'll take the trace of pi of alpha, and this is this trace, and basically this is the invariant, but we have to fiddle with it a little bit, I think. So I can get a minus t plus 1 to the root t. There's some fudge factors, the n minus 1. So we have to divide by it. No. It was right before. I'm going to write it as its third form. Times root t. The main thing, the only real thing to remember here is this part here, which is simply trace of pi of alpha. And the rest is just fudging. And this is t minus root t to the e of alpha. I think it's minus n. I don't know. Look this up in any thing on the Jones polynomial. This is an invariant of alpha hat. So we just have to check that this depends only on alpha hat. And that's very easy. It's just got to be invariant under the two two Markov moves. This is manifestly invariant under the type 1. And then this property, this Markov type property here, this independence, is just a change of variables, because instead of having W E n plus 1, we'll have W sigma n plus 1. So we have to simply write it out so that this n is plus or minus 1. So this actually doesn't change when you stabilize by that. But this exponent, this E of alpha, is the exponent sum. When you write alpha as a word on these braids, on the generators, you get this number, which is the sum of all of the powers of the generators. It's also the same as the abelianization of the braid group is the integers, and it's the integer that you get when you abelianize a braid. I think this is, I forget what I think it's minus 6. Anyway, a few examples, and you find that it's a Laurent polynomial in root t. And in fact, if the number of components is odd, the which is the case of knots, it's a Laurent polynomial in T. It's called the Jones polynomial nowadays. Now I write it VL of T. V is supposed to be for von Neumann, because the whole thing goes straight back to von Neumann. So, an example. Well, we could do the figure 8, but that would be a bit painful. But we can very easily do these so-called 2n torus knots. Because this is sigma 1 to the n. And remember, sigma was represented as TEI minus 1 minus EI. So this is, so sigma 1 to the n is T to the n EI plus minus 1 to the n 1 minus EI. And since we're just out of time, let me leave it as an exercise for you to finish the calculation for when n equals 3. This is the trefoil knot. After you've done this, well, it's very simple. You've got t cubed here and a minus 1 here. You take the trace set, just multiplying by t over 1 plus t squared, which is a trace of the EIs, and then doing the algebra, throwing in that fudge factor, and you get t plus t cubed minus t to the 4th. And that's the Alexander polynomial, was t inverse minus 1 plus 2. Okay, so in particular, this one has the advantage that when t goes to t inverse, which is obviously the mirror image, it actually detects it. So this polynomial shows immediately that this trefoil knot and then all of these 2n torus knots are actually different from their mirror images. And while that, of course, was known, you couldn't just deduce it from the Alexander polynomial. Okay, so that'll do it for today. Now I'm still only 2 lectures behind, I think. So. The plan, so let me tell you the plan for the next lecture, is to give a point of view due to Lou Kauffman, very fruitful point of view on this polynomial, which allows you to define it in a very elementary way and do the calculations in an even simpler way than this. Not always as powerful, but certainly very elementary. And then the Kauffman idea was so lovely, if you like, that the hope was that you could actually use that framework of the Kauffman polynomial to describe the entire subfactor. So it was to pull back this Kauffman idea into subfactor theory and get description of subfactors. And that's what will give us the theory of planar algebras. Okay, so that's Wednesday's work.